Hey everybody, it's 15HARBIN here to do video notes 8.2. So we're going to be able to do all this stuff eventually. Alright. So hopefully you get why I'm playing this song. Alright, so we talked about heating curves already. There's two major sections, a slanty part and a flat part. So slanty parts are a change in temperature, and so it's a kinetic energy change. And then the flat parts are changing in phase, so it's a potential energy change. And that's when the states are changing. States, phase. Changing phase, changing state. Okay? So make sure you can interpret a heating curve and know what's going on where. So, slanty parts, single state, kinetic energy change. So it could be a solid, liquid, or gas. Flat parts are changing states, so solid to liquid or liquid to solid. Liquid to gas. I'll put that under boils. Liquid to gas. Condenses is gas turning back into liquid. Okay? Make sure you can interpret that. So, can you make a heating curve? Well, let's see. This substance is called yum. Alright? Want to make a heating curve? Well, let's make it specific. We need these two things. The boiling point is always the higher temperature. Okay, so this is going to be temperature in degrees Celsius. And then the melting point is the lower one, 155 degrees Celsius. So we want the whole heating curve here. So down below we got solid, slanty solid, single state, flat line solid to liquid, phase change. Slanty line, single state liquid, liquid turns to gas, and then slanty part gas, all the same state. Okay, so why is boiling longer than melting? So here's boiling, it's a longer line than melting. Well, it's because it's going to take more energy to break the intermolecular forces between liquid molecules and turn them into independent molecules than it takes to change the solid molecules into a liquid, which have a little more space, but they're still pretty close. Okay, so boiling is longer than melting because it's more. This one is increased potential energy more to move the molecules further away from each other. Okay, here's all the phase changes you need to know. Solid to liquid and liquid to solid are solid to liquid and liquid to solid. Okay, so they're reverse of each other. The melting point for water is 0 degrees. The freezing point for water is 0 degrees. So what's the difference? One, you're adding heat in to change it to a liquid. The other one is you're taking heat out to change it to a solid. Okay, boiling is not evaporation. Boiling and condensing, for water, it's 100 degrees Celsius. So what's the difference? One, a liquid's turning to a gas. The other one is a gas turning into a liquid. But it's still at the same temperature. One, you're adding heat in. One, you're taking heat out. These are also the opposite of each other. Okay, but sublimation is a solid going directly to a gas. Deposition is a gas going directly to a solid. Okay, it doesn't happen for every substance. Okay, evaporation is not boiling. If you get out of the pool and you say the water boiled off of you, you'd be lying. Okay, if you get out of the pool and say the water evaporated off of you, you'd be telling the truth. Okay, so what's the difference? Okay, evap is when the surface molecules leave. So everything else is cooler. Okay, that's like you. There's your arm, your surface molecules leave, and then you're cooler. Right? Boiling, every molecule in this liquid can turn into a gas. So you could have a molecule down here turn into a gas, so you get a bubble, and then another bubble over here, so that these liquids are turning into gas all the way through. Okay, so evaporation is surface. Okay, boiling is all, and then it's at boiling point. Okay, all right. So boiling in point in atmospheric pressure. So here's a liquid. You have regular pressure, air pressure pushing down on liquid. If this liquid needs to turn into a gas, then these molecules have to overcome the pressure pushing on them. So the boiling point is when the pressure pushing down is equal to the pressure pushing out of the liquid from the new gas. Okay? So boiling point changes with atmospheric pressure. If you take a pressure cooker, you're putting high pressure above the liquid, so then this will stay liquid longer. It won't boil at its boiling point, it'll boil higher. Okay, you take the lid off, then it gets to its regular boiling point, where you go up into the mountains and you make a pot of water Okay, and you want to boil it. Well, there's less pressure pushing down, so the temperature at which atmospheric and vapor pressure are equal is lower. Okay. All right. So specific heat, what is it? Specific heat is abbreviated C, and this is a definition. Make sure you know the definition of specific heat: energy to change 1 gram of a substance by 1 degree Celsius. Okay. So let's talk about cement and the grass. All right. Cement, if you stand on it, the heat goes into you pretty quickly because it has a low specific heat. The grass feels nice and cool because it has a high specific heat, a high C. All right. Oven and oven rack. Okay, so say you heat up the oven. Everything in the oven is at 350 degrees Celsius because you're going to cook a pizza. If you put your hand in the oven at the gas part, okay, you won't get, the gas doesn't transfer its heat to you, so gas has a high specific heat. But if you grab this oven rack, ow, 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 this, you would get burned right away because it has a low specific heat, so the heat transfers into you. Okay, how is this going to help us? Well, that's why we use metal pans, glass pans, regular pans, and cement to transfer heat quickly. So we want heat to go through it, so we use a low specific heat. Okay. If you want heat to be stopped or take a long time to change the temperature of something, use something with a high specific heat, high C. All right. So we use insulation to keep stuff insulated. Coats. Air is a pretty good insulator. Grass is a pretty good insulator. Okay. So how much heat does it take to warm something up? Well, you want to warm something up, you need to know things like the mass. Okay. You need to know what it is. So it's specific heat. Specific heat. And you need to know, well, how much do I want to warm it up? So you need to know what temperature you're trying to change. So the equation you have to know is Q equals MC delta T. Q is heat. Heat can be calories or it can be joules. M is mass. Mass is going to be in grams. Okay, so G. C is specific heat. Specific heat is calories for every gram degree Celsius, or it could be joules for every gram degree Celsius. And so now we can compare things. Specific for a substance, you gotta look this up for what you're trying to find. Delta T is change in temp, so it's a difference. Change in temp, so it's a difference. All right, temperature difference. Okay, so here's a problem. 223 joules of heat. Well, that's a Q. 19 grams of water is an M. C is a specific heat. So what is it that we're trying to find here? We're trying to find how much does the temperature change. Find delta T. So let's plug in the Q, 223 joules. Plug in the M, 19 grams. Plug in the C, 4.184 joule, 18 joule per gram degree Celsius. And so delta T is what we're looking for. So if we want to solve for that T, we got to get rid of this by dividing 19 and 4.18. That all goes away. And on this side, we have 19 and 4.18. So our answer is 2.81. So delta T equals 2.81. And now what's the unit on the top one is joule. Down here is grams. Down here is Celsius. Up here is joule. Down here is grams. And down here is joules per gram degree Celsius. So grams cancel grams, joules cancel joules, and we're left with Celsius. So 2.18 degrees Celsius. Okay, so calorimetry. Key idea, write this down. Key idea. Heat lost equals heat gained. What? Heat lost equals heat gained. What? Heat lost equals heat gained. Okay, that's a key idea of calorimetry. All right, so what do I mean? Well, if I put a hot piece of metal and put it in cold water, what's going to happen? Well, the water's going to get warmer and the metal's going to get cooler. Okay, why does the water get warmer? Because the metal gives it heat. Why does the metal get cooler? Because the water takes its heat. So the key idea is that the heat, the Q from the water, the heat that the water takes in, is going to be equal to the heat that the metal gives off. So we can use this to help figure out any of these variables that are missing. Okay, but this is the Q of heat gained by water is equal to the heat lost by the metal. Okay, so this is the key idea to calorimetry because heat loss equals heat gain. So what does that mean? Well, here's some water data. Here's some metal data. We should be able to calculate any of those missing things. So remember, Q for water, the heat of the water is the mass of the water times the specific heat of the water times the change in temperature of the water. But that has to be equal to the heat of the metal, which is equal to the mass of the metal, the specific heat of the metal, and the temperature change of the metal. So let's see what we can figure out. We can figure out the heat the water takes it. So that's going to be equal to the mass of the water times specific heat of water is 1.00 calorie per gram degree Celsius. Notice I'm using the units of calorie now. Change in temperature is 24.1 minus 20.1 is 4.0 degrees Celsius. So the heat that the water loses, I'm sorry, water doesn't lose this heat, water gains this heat, is 150 calories. 150 calories. Alright, so you're saying to yourself, hey self, what about the metal? Well, the heat the metal takes in is that. So the heat of the metal has to be 150 calories. But that has to be equal to the mass of the metal, 86.2 grams of metal, times the specific heat of the metal. But wait, we don't know it. We don't know it. So we don't know the specific heat. Temperature change of the metal is 98.9 degrees Celsius minus 24.1 degrees Celsius. The temperature change of the metal is 74.8 degrees Celsius. Alright, so what does this mean? Well, this means that this C is going to be equal to dividing by both of those numbers to get rid of them, by, but we have to take the 150 and divide it by 86.2, and that was grams, and 74.8, and that was degrees Celsius. So our heat, this is not Q, this is C, because the Q was the 150. So what our final answer is C. 150 divided by 82 divided by 74 gives us 0.023. What's the units? Calorie per gram degree Celsius, which is specific heat of the metal. So we just found out specific heat of the unknown metal. So we can use calorimetry to do that. Alright, so to review, make sure you can draw a heating curve. We'll keep practicing. Remember, temperature is constant during phase change, flat line. Evaporation is not equal to boiling. Know your specific heat, CCC. Okay. Calorimetry is a measure of heat in a reaction. Heat lost equals heat gained. Helps us solve calorimetry problems. Make sure you know that. Okay. Peace out, and make sure you got this information down. All right. Hopefully this works. The second time I'm taping this because I want you guys to learn. All right. Peace out.